Hi geology students, welcome to chapter 4 on extrusive igneous rocks. Chapter 3 was about intrusive igneous rocks, so we're going to be looking at extrusive igneous rocks today. So you can see the outline for this chapter in front of you here. I want to take a minute to explain something about this chapter and really about all of my video lectures. From time to time, you see YouTube links in these slideshow presentations, and of course, they are not linkable when you're watching this presentation as a video. Understand, please, that all of these YouTube links will be, they are in each week's module. I have a separate section for them, and usually they're on there for good reason. They are valuable things to watch, and they're usually fairly short. They're usually 4 minutes or left. This week, there's quite a few of them. Not all of them are going to be linked in here, so please be sure to check out in this week's module all of the volcanic links. There's some important demonstrations of stuff there. So in this part 1, we're going to cover several of the topics that you see there. And we're going to start off with, well, just what are extrusive rocks? Extrusive rocks are a type of igneous rocks. They form from cooling of molten rock. The big difference between extrusive rocks and intrusive rocks is where that molten rock cools. So that's the big main difference in origin. But the difference in location, the difference in where they cool, happens to the conditions are quite a bit different below ground versus above ground, and this leads to a difference in cooling rate, which in turn leads to a difference in texture. That's the key. The location they form leads to different cooling rates, which leads to different textures. So we'll start off looking at this particular diagram again. So we looked at this last chapter showing that when you have molten rock and it's under the ground, it is called magma. And magma below the ground will cool to form intrusive rocks. If that molten rock makes it to the surface, then it's no longer called magma. It's called lava. It's still molten rock. It's still the same stuff, but we call it lava once it is above the ground. And this stuff cools above the surface to form extrusive rocks. So the main difference here is that it's much hotter below the surface than it is at the surface. Even on a 110-degree day, it's much hotter below the surface, which means that surface molten rock cools several orders of magnitude more quickly than intrusive rock, than rock below the surface. This may take millions of years to cool. This will take a day or two at most to cool, usually. Now, lava flows on the surface are not the only way that we get molten rock cooling at the surface. Sometimes the molten material is erupted into the atmosphere. When that happens, we call this pyroclastic material, which means fire broken. But when this molten rock cools very quickly in the atmosphere, it still forms extrusive rock. So as long as it's cooling above the surface, it is extrusive igneous rock. So this is an example of a pyroclastic eruption. You're not seeing much in the way of lava flows going down the slopes of this volcano. Instead, you're seeing mostly pyroclastic eruption here, still a type of extrusive volcanic activity. In fact, the term volcanism simply means eruption of molten material out of the ground. So what are the effects of volcanism on humans? There are a whole lot of them. I'm not going to dwell on them. I'm going to list them. But volcanoes are responsible for our oceans because they moved the water from our mantle that had been there for a long time, and through the process of eruption, moved that water into the atmosphere, which then fell to the ground and filled up the low areas as oceans. They're also responsible for part of the makeup of our atmospheres. Big eruptions affect sunsets. They make some spectacular sunsets. Large eruptions can cool the weather temporarily, and they also create land. If you take Japan, Indonesia, Hawaii, these are all places that would not exist. They would not be above sea level if not for volcanic activity. So volcanoes build land. So there's several effects on humans. But the most in-your-face effect, and the one that most everyone's aware of, is that volcanoes are extremely destructive. For example, the burial of the city of Pompeii. That's what people remember about volcanoes, is they're extremely destructive and fatal in many cases. But not all volcanoes erupt the same way. There's basically two manners of eruption. There's two styles of eruption. There's many more than two styles, but you'll find that I'm a lumper, and I'm lumping all these styles together into two styles. We're going to call these styles explosive and effusive. And another term for effusive would simply be non-explosive. So let's look at this real quick. This is an explosive eruption. Mount St. Helens, the most famous eruption in U.S. history, because it happened after 6 weeks of buildup, and the whole scientific community, as well as a great deal of just the regular Joes and Janes communities, were watching this as it happened. So it was an explosive eruption, pyroclastic material. And here's a good link. I'll have this linked in our module, so don't worry about that, but that'll show you a good example. There's some really good things to see about that. This is an example of an effusive eruption. Now, you may try to counter me by saying, Lowry, that stuff is being blown up into the atmosphere, but not very far. And it's very quickly falling down to the ground. So really, mostly what is happening here is the lava is coming out of the ground relatively peacefully, and you wind up having a whole lot of lava flows on the ground instead of being blown up into the atmosphere. So we're calling this an explosive eruption, and we're calling this an effusive eruption. If we knew what to expect for each volcano, then it would be helpful for us to prepare. So I've got these side by side, although I used a different Mount St. Helens figure here on the left. But on the left, we have an example of an explosive eruption. So what makes some volcanoes erupt explosively and some non-explosively? There's a lot of factors that influence this, but none more than the viscosity of the lava itself. And viscosity means thickness. Things with high viscosity mean that they are really thick. So liquids with high viscosity might include something like peanut butter. It's extremely thick. Ketchup is pretty thick. These have high viscosity. And something with low viscosity would be water. Water, blood, 7-Up, these things have low viscosity, low resistance to flow. Whereas things like peanut butter and milkshakes have higher viscosity. Some magmas behave like those high viscosity things that we mentioned. And with those magmas, all magmas, let me back up a little bit, all lavas contain gas dissolved in them. But with high viscosity magmas, they are so thick that the gas does not escape easily. And this allows gas pressures to build up really, really high, so that when they do eventually escape, and they will eventually escape, they escape in an explosive manner. Now, thing is, if we get a sample of the lava to test its viscosity, well, it's too late. The volcano has already erupted anyway. So is there a way that we can tell how the viscosity of a lava before it erupts? Possibly, because the several things that affect viscosity, but the one that affects lava viscosity more than the others is the silica content. Magmas with high silica content are thick and allow gas pressures to build up really, really high into explosive eruptions. Well, now we're dealing with familiar terminology. That's describing felsic magmas. So felsic magmas tend to erupt explosively. And the opposite is true for effusive eruptions and mafic magmas. So effusive eruptions are the result of low viscosity magmas. Runny magmas do not trap gas as well, so the gas escapes easily before pressures have a time to build up to dangerously explosive levels. And what makes lava's low viscosity? Again, several factors such as temperature, but mainly the silica content. Low silica magmas, in other words, mafic magmas, tend to have low viscosity. They're runny. So on the left, we have thick magmas that erupt explosively, and on the right, we have thin, runny magmas that erupt effusively. So the past eruptions are very frequently an indicator of what the future eruptions will be like. Remember that mafic rocks are dark, and we see that these effusive eruption products are quickly cooling into dark rocks, and felsic products are light colored, and they're frequently cooling into light colored rock there. So sometimes just the color of the volcano itself or its past products is a clue to how it will erupt in the future. Okay, that's the end of part one. In part two, we're going to look at the several hazards that that the volcanoes produce. YouTube is very important in part two. Not going to watch it during these live videos, but I urge you to watch them, the videos that I will post in this module.